Hello, welcome you all for the next topic on unsteady state material balances. In this session, we'll learn how to do the material balance under an unsteady state condition for the case of batch distillation. Note that in distillation, we do not come across reactions, unlike CSTR. In CSTR, we saw the reaction cases. Here, we do not get a reaction. Okay, let's look into the concept of developing the unsteady state equation using a numerical. Here is the numerical. In this case, we are having a batch distillation numerical where some numbers as well as the concept or the components of that it's clearly given. You can pause the video, read the problem, or you may note down the problem and get back. Alright, I assume that you have read the whole problem. Let me simplify it for you. We have a distillation unit. In this two components are there, propane and butane. The temperature at which it is present is 135 degrees Celsius. In total, put together, you have 10 kilomole of the mixture. In this 10 kilomole, you have butane composition, XS, it is the notation given, that's around 0.30. So we'll add additional mixture that is the same with the same composition, XF is equal to 0.3 is fed at the rate of 5 kilomole per hour. So it's a continuous process. So continuously we are adding 5 kilomole per hour of the feed with the same concentration as the original. So this was at the beginning. Then we start adding at a 5 kilomole per hour rate from t is equal to 0. Now the situation changes dynamically. So it ends up with an unsteady state situation. If the total volume of the liquid in the distillation unit is constant with respect to time, we don't have to mention that, but dB by dt is equal to 0 with respect to this particular statement. Concentration of the vapor from the unit, not denoted as XD. Okay, so the vapor of, in fact, it's for butane, is related to the distillation unit concentration XS. So the butane is present in the within the distillation unit, we call it as residue, as well as it is present in the vapor, that's the distillate. The relationship between the concentration of butane in the vapor to the liquid stream XS is given by this equation, that is XD is equal to XS by 1 plus XS. So that's the relationship between the two things. Now the question is, how long will it take for the value of XS, the concentration in the residue, that is a liquid stream, to change from the initial value 0.3 to 0.4? So it may have to increase, the concentration may increase. How long will it take? So what is the steady state value of XS in the distillation unit? That's the second question. So this will have occur under unsteady state condition, 0.3 to 0.4. Slowly it will increase, and after some time it will reach a steady state. All right, so once it reaches a steady state, the concentration of the butane in the residue stream, that is in the liquid stream, will remain constant, right? So that's called as steady state condition. So at that steady state condition, the value of XS is what you have to find out. So there are two questions. So let's develop the balance equation, substitute and solve the problem. So here is the distillation column, into which we have initially fed 10 kilomole of the liquid stream, total propane and butane. Of this, butane is excess 0.3, right? That's the constant mole fraction. Continuously we are feeding the flow rate, that is 5 kilomole per hour. We'll make an assumption the vapor flow rate is also same. In fact, we can prove this because if you consider the density, if you make a total balance, which is not mentioned in this problem, you can make a total balance here. So when you make a total balance, the total quantity comes in minus the total quantity goes out. The rate of total quantity that goes out is equal to the accumulated term, right? So the total quantity will have a density rho I, exit will have a density rho naught. So let me assume that rho naught and rho I are same if that's the case, and the accumulation will be d by dt of rho v, as we have done in CSTR. Since the rho is same, we can cancel out, and it's clearly mentioned dv by dt, constant volume case, dv by dt is equal to 0. So there is no accumulation of volume. In terms of volume, it remains constant. So keep in mind, whenever there is a constant volume, so the flow rate will be equal. The inlet and outlet flow rate will be equal in these two cases. Here it is not volumetric flow rate, it is a mass flow rate. Hence, total density, the density input and output are not necessary because it's not a volumetric flow rate, it is a mass flow rate. In simple, it is Fi minus F naught will be equal to d by dt of m into rho. Alright, so if you assume that rho and v are both remain constant here, so Fi will be equal to F naught. Even though it is not given, we can make an assumption since the volume remains constant. Then coming to the inlet, you have adding oh yeah, this is an error here. So xf is equal to 0.3. It should be 0.3, I guess, not 0.3. So make a correction. Then the output concentration xd is xs by 1 plus xs. Alright, so this is a relation, exact values not given. It's a function of this xs. Remember, this xs changes with respect to time, as well as xd also changes with respect to time. That is called as unsteady state situation. But after some time it will reach a steady state condition, and that is called as a steady state solution. Now let's do a butane balance. So only the butane will consider how much butane comes in along with the inlet stream, how much goes out in the distillate portion, and that remaining portion will get accumulated in the residue. So as we know, this Fi and F naught both are molar flow rate. So that's the total molar flow rate. A fraction of that, if you multiply, you get the molar flow rate of the butane. So you have xf into Fi, this is the inlet condition, F naught outlet, and xd, that's the exit concentration. That will be equal to the accumulation of butane. How we do the accumulation analysis? D by dt of, that is with respect to time, accumulation, whenever you write rate of accumulation, it's always d by dt of mass. Here it is the mass of butane. Total mass is m. Of that, the composition of butane is xs, that is mole fraction of butane we have to consider. So this gives us the total mass of the butane. Now since m is constant, initially we added, and that remains constant throughout, so I can take that m outside. Now substitute and simplifying it. So that is xf is equal to 0.3, Fi and F naught both are 5 mole per kilomole per hour. Then xd, that is xs by 1 plus xs, that's the equation given to us. M have taken outside 10, and this xs, which is a variable with respect to time, remains as it is. So upon simplification, uh, and rewriting the terms, so let's simplify the whole term, because this 10 I have taken out the other side, divided, right? You can pause the video and you can scroll through up to this particular point. So here is the final simplified version of that. You get 0.15 minus 0.35 by 1 plus x is equal to dx by dt. Now we'll have to integrate this equation with respect to x's and t. So we'll separate out the term. All those terms which are related to x's, we'll take it on the other sum. In fact, all these terms are related to x's, so the dt will go on the other side, and these terms will come on this side. That is 1 plus x's divided by 0.15 minus 0.35 x's dx. We'll have to integrate this equation. For integration, we'll have to use some strategy so that we can simplify this equation. It's a non-linear equation, right? So you have numerator and denominator both x's is present, so we'll have to simplify it carefully. So let's go ahead with the separation of variables technique. So first we'll divide this particular component, 1 divided by the denominator plus x's divided by the denominator. So let me call it as equation 1, because this particular term will have to simplify it further, because we will not be able to integrate directly as it is. So let us work on this particular terminology, whereas this is easy to integrate. This one will simplify it further. Okay, the same term I have taken it here, xs divided by 0.15 minus 0.35 xs. Let us make a modification of this, right, called as separation of variables. After separation of variables, we will get this particular equation. How do we get this? Let's do this way. Let me take, just for simplicity purpose, xs I'll replace with the x. Here it is written, x is equal to xs, a is 0.35 and b is 0.15. So how can we write it? X divided by b minus ax. This equation is the second equation in integral form there. So I'll write it as x by b minus ax. Now we'll have to simplify that. So how do we simplify that particular term? We'll have to convert the numerator and denominator in a similar way. So that is, the numerator also I want it in the form of b minus ax, right? How do we get that? So numerator and denominator both I want it in the same format, but here it is only x. How can we get it? You can multiply it with the minus a by a, right? Minus a by minus a, so one of that it will come out, and one more term you can add and deduct, that is minus b by a plus b by a. So if you look at the numerator, the intention of getting done is this variable where it is, that should look alike at the denominator. You should get one term in the numerator, or in simple way in the numerator, this is the way I can tell you the easiest way out. Just write the numerator and denominator same, right? So here it is. So numerator and denominator I have written it same, right? Exactly like this. Denominator is exactly same, okay, but this numerator I have modified it, right? Now I have to write some terms in such a way that when I simplify the numerator I should end up with only x. How can I do this? So if I had to cancel out this a, I had to multiply it with the minus 1 by a, or otherwise I should say I should divide this by minus a. So that's why I have done minus 1 by a. Then I have this b also. I have to, this is b plus b, right? So I have to cancel it out, and along with that I have minus 1 by a. So what I'll do is I'll make plus b by a. So when I take plus b by a and minus b by a, it gets cancelled out, 0. Then minus 1 by a into minus ax, I get plus x. So I end up with x. Alright. Now that will simplify with the values and resubstituting b minus ax, right? So this b minus ax, I can simplify this term into two parts. So this numerator I can divide into two parts, one part like this and second part with a constant. So this b minus ax gets cancelled out, it ends up with a minus 1 by a, which is minus 1.35, minus 1 by 0.35, plus the second term b by a divided by b minus ax, right? B by a divided by b minus ax. So if you look at the equation here, numerator and denominator both you had x, which is a variable, right? Now if you simplify this equation into by using the separation of variable, if you look at it, numerator does not contain any x, the denominator only has the x, that to one equation, right? So this is easier to integrate compared to this one. That is why we make this modification. Let's get back to our equation 1 where we had started with. So we had this equation, right? This equation we had. So this was the original equation we had. Now this particular equation we have separated into two variables this way, right? This is the equation we have got just now. We'll replace this with this equation. So it is minus 1.35 0.428 by 0.15 0.35x. Yeah, it's everything correct. Now let's go ahead and do the integration. So how do we do the integration? Look at this, denominators are same, numerator I can club, right? So 1 plus 0.428, denominators are same, I'll club it. 1.428 divided by 0.15 0.35x minus, yeah, that's a constant, integrate. Now while I'm integrating, I need to take the limits of integration. How do we take it? Now let me say that the entire unsteady state process started at t is equal to 0, because that was the time where till when everything was proper, the constant, the still was constant and no inflow was there. Suddenly you started an inflow, right? So the coming in concentration will affect the still, that's the residue component will be affected starting from 0th time. After that it goes on changing up to some variable time t. I do not know the value of t, so I'll keep it as t as it is, so 0 to t. At the beginning, when t was 0, the concentration in the still was xs, original concentration. Let me say it as xs naught, xs at t is equal to 0, right? That is 0.3. After some time, it will change to xs. You can replace with the xs. Here in this case, we are asked to find out at how much time is required to go up to 0.4 concentration, mole fraction, right? So if it was unknown, still you can write it as xs, that is xs at t is equal to t. This is xs at t is equal to 0, right? So these are the two limits of integration. Now we'll have to integrate this particular equation. How do we integrate? So this particular equation 1.428 divide, it is ln of, it's as good as 1 by a minus bx, right? It is 1 by a minus bx. How do we integrate it? It is 1 minus 1 by b ln of a minus bx, right? So 1.428 is a constant that remains there, so minus 0.35. So let me repeat it. While integrating this, you get, it is in the form of 1 by a minus bx. when you integrate it, you get minus 1 by b ln a minus bx. That's the format of integration. Whereas this one, it is just a constant, so it is x by 0.35. Now wherever that x is there, you have to substitute the values upper level of integration and lower level of integration, upper limit, lower limit, 2 times, right? So on the other hand, it is t minus 0, so it is t, simply t there. So when you substitute xs, look at here, so it's ln of 0.15 remains as it is, minus 0.35 into xs. So wherever that xs is there, put the limits, 0.4 minus 0.3, upper limit minus lower limit, minus here upper minus lower limit divided by 0.35. Simplify the entire term, you get 5.8 hour. So what it means is it takes 5.8 hours to reach the concentration mole fraction 0.4 from 0.3 in the residue stream, right? So that was the one question. Second one, it was under steady condition. Once the steady state is reached, that means it will be after 5.8 hours. Okay, so after 5.8 hours, after some time, the concentration will remain same. Need not be some, we have to find out that how much it is. We'll have to find out. So at what at that particular time, a steady state condition, the concentration of butane in the still remains same. As I told you earlier, under steady state condition, the accumulation term goes 0. In our equation, the accumulation term we had dx by dt, right? So that will go 0. Just substitute accumulation is equal to 0. This is the equation we had there earlier. Fixf minus f naught xs by 1 plus xs is equal to, we had the term for, that is m into dx by dt, right? So that was 0. So it is simply an algebraic equation. It is not a differential equation. So substitute here. So in which at this point, remember, xs is unknown and it's called as a steady state solution. So simplify this algebraic equation. So when you simplify this algebraic equation, xs will be equal to 0.428. So this is the method how you can solve and algebraically. Alright, so simplifying the terms on both the sides, xs will be equal to 0.428, and you see that it reduce the residual concentration will be 42.8 mole percent. And previously we saw that to reach 0.4, that is 40%, right? Mole percent is 40 for butane. To reach 0.4 it took 5.8 hours, and to reach 4, that is 0.428, it will take some more time, more than 5 hours. So that means after 5 hours plus it will reach a steady state condition. If at all you would like to find out how much exactly the time required, you can use the same equation. Now instead of 0.4 you could use 0.428. Same equation, same solution here, right? Instead of 0.4, if you use 0.428, that's the steady state concentration, right? That's the steady state concentration. So if you use that, what do you get? You get t is equal to some time, a time you'll get after calculation 0.3 to 0.428, and that is the time required to reach the steady state. This is very important in analysis of unsteady reactors or distillation units. How much time is required to achieve the steady state condition. Yes, that's it for this class. Thank you.